What if your path through space-time, your actual physical journey, wasn't just a straight line forward? What if it kind of looped back around, bringing you right back to where and when you started?
That's the essence of it.
Today, we're doing an intellectually curious dive into one of the most mind-bending ideas from Einstein's general relativity. Closed time-like curves, CTCs for short.
Right. And the core idea, technically, is a closed world line. It means a path for, well, any physical object where it returns precisely to its starting point in both space and time.
It sounds like pure sci-fi, but this isn't just speculation. The math started showing this possibility way back 1937 with Willem van Stockham.
That's right, with rotating configurations. And then, more famously, Kurt Gödel in 1949 found a solution, a whole model universe where these CTCs were, well, everywhere.
So our mission today is to unpack how physics even allows for time to loop like this, and crucially, what that implies for causality, for cause and event. Okay, let's start with something fundamental. The light cone. We usually think of our future possibilities as being contained within this cone, right? Time going up, space across.
Exactly. The edges of the cone represent moving at the speed of light. You can't go faster, so your future path has to stay inside that cone within that 45-degree angle relative to the time axis.
But general relativity complicates this picture.
It really does. Intense gravity or rapid rotation actually warps space-time itself. And this warping can physically tilt the entire light cone.
Tilt it.
Yes. And if the gravity or rotation is extreme enough, the tilt can go beyond 45 degrees.
Wait, so if it tilts past 45 degrees, what does that mean for the direction of time?
It means the direction that feels like future inside that tilted cone actually points towards locations that someone outside would see as, well, simultaneous or even in the past relative to the starting point. Space-like separated, technically.
So your forward in time is now pointing sideways or even backward from an outside perspective.
Precisely. And a closed time-like curve is formed when you have a sequence of these tilted cones that essentially guides a path in a loop right back to the starting space-time event. An object just following the curve in freefall ends up where and when it began. Now, these aren't just mathematical curiosities, though some examples are maybe a bit contrived. They appear in specific, exact solutions to Einstein's field equations.
Like the Gödel universe you mentioned.
Yes, the Gödel metric, sometimes called Gödel lambda dust. And there's also the Tipler cylinder, which involves an infinitely long rotating cylinder. Pretty exotic stuff.
Okay, infinitely long cylinders sound unlikely, but aren't there more realistic scenarios where CTCs appear?
That's the really interesting and maybe troubling part, the interior region of the Kerr metric.
Which models a rotating black hole. A realistic object we think exists.
Exactly, an uncharged, rotating black hole. The standard mathematical description of its interior contains CTCs. Now, many physicists suspect these might be mathematical artifacts, that quantum gravity or something else might prevent them.
But they're in the solution.
They are in the classical GR solution, and their presence directly implies the theoretical possibility of traveling backward in time, which immediately brings up paradoxes.
Right, the grandfather paradox. If you go back and, prevent your own grandfather from meeting your grandmother.
Then how were you born to go back in the first place? It's a logical contradiction. The main proposed way around this, theoretically, is the Novikov self-consistency principle.
Self-consistency, meaning?
It basically states that if time travel into the past is possible, then physics must conspire to prevent paradoxes. Any action you take in the past was already part of the history that led to you going back. You can't change the past. You can only participate in it in a self-consistent way. The universe enforces consistency.
Okay, that's a fascinating idea. We need to take a quick break, but when we come back, let's talk about what happens if that principle doesn't hold and the deeper threat to causality. We want to thank our sponsor, embersilk.com. For anyone looking into AI, whether for education or integrating it into your systems, Embersilk has the answers. Check them out, embersilk.com. All right, we were talking about the Novikov principle ensuring consistency. But what if CTCs exist and things aren't necessarily self-consistent? What's the implication then?
Well, the most profound consequence is arguably the breakdown of determinism, of causality, as we usually understand it.
Meaning, knowing everything about the universe right now isn't enough to predict the future.
Exactly. If events can loop back from the future via a CTC and influence the present, then the present state isn't solely determined by the past state. Something new, seemingly uncaused from the past perspective, can emerge.
So prediction becomes impossible past a certain point.
Correct. There's a concept called the Cauchy horizon. It's essentially the boundary in space-time beyond which predictability fails because of the influence of these CTCs. You could have perfect knowledge of everything on a surface before the horizon and still not be able to calculate what happens after it.
That sounds fundamentally problematic for physics. Is there a way physicists try to avoid this?
Yes, the most famous idea is Stephen Hawking's chronology protection conjecture. It's basically a conjecture, a strong hypothesis, that the laws of physics themselves, perhaps involving quantum gravity effects we don't fully understand yet, will always intervene to prevent CTCs from actually forming on macroscopic scales.
So nature forbids time machines.
That's the hope behind the conjecture. And there's some support from quantum mechanics, too. Quantum formulations involving CTCs often lead to really strange predictions, like being able to violate the no-signaling principle or create entanglement essentially for free, which seems deeply wrong.
It suggests CTCs might just be too disruptive to reality as we know it.
It really forces a fundamental question. Is the universe strictly causal in the linear way we experience it? Or could these self-contained loops, these regions where events cause themselves perhaps, be a genuine, if bizarre, feature of space-time geometry allowed by gravity?
So the big takeaway is that CTCs push us right to the edge of our understanding of time and causality.
Absolutely. Are they mathematical warnings or hints of a stranger reality?
Which leaves us with a really interesting question for you, the listener, to ponder. Imagine if CTCs are proven to exist, but maybe only deep inside black hole event horizons. So they're real, but completely hidden from any outside observer. Would you consider that kind of space-time to still be, well, causally well-behaved from our perspective, since we could never actually see or interact with the time loops? Something to think about. That's all the time we have for this deep dive into the loops and paradoxes of time. Thank you so much for joining us. If you enjoyed this, please subscribe to the show and maybe leave us a 5-star review. It genuinely helps get these discussions out there.
It really does.
And remember to check out our sponsor, embersoak.com, for AI education and integration needs. We'll catch you on the next exploration.